Okay. For the stoichiometry, the balanced chemical equation looks like this. It's just barium ions like sulfate ions, and it forms a precipitate of barium sulfate. So for every mole of barium sulfate precipitate that we get, 1 mole of sulfate ions were present. We're going to get a lot less than a mole of barium sulfate, and so we'll have a lot less sulfate. But once we figure it out stoichiometrically, this is just your grams of barium sulfate to moles of barium sulfate to moles of sulfate to grams of sulfate. Just your standard stoichiometry calculation: grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. All right, so the formal report for this. The due date will be TBA. It's going to be much further. So first get your calculations done, and then we'll look at the data. And it's a formal report. Formal report is just, we want to have a certain format, and that format, and I'll post a handout for this. There's something called an abstract, introduction, experimental section, or methods and materials section, experimental, and a discussion section. And so those are the components. So we'll be looking at these one at a time. All right. For today, we are doing another unknown analysis, but this one's not going to be a formal report. So for the titration will be due 1 week after we finish it, which will be next week. And so you're going to be completing this lab before the sulfate lab. Now for the titration, we need to complete part 1. Are you getting decent precision with part 1? That is, are you getting from the, remember, we have to have the percent difference. We had the percent difference in volume here. And we needed the percent difference in volume to be less than what? 0.5%. We could do it or molarity. In part 2, it's a bit different, because in part 1 we always use 25 milliliters of acid. 25.00 milliliters of acid. In part 2, you're going to have different samples of acid. You're going to have an unknown solid acid, and it's too much hassle to make every sample the same size. Are you going to weigh out 3 identical samples? No. In fact, we're just going to have the target. The target mass is going to be on the bottle itself. And so when you get your unknown vial, you'll have some kind of target mass. And this target mass will be between, let's say, point X to point Y grams. And so what you're going to do is you're going to weigh it. You're going to weigh it to point Z grams. And so just get it anywhere within that target. The target mass is so you don't have to do a trial titration. If you didn't have the target mass here, let's say you weigh out a sample and it's too little. Too little means you're using less than 10 milliliters. That only gives you 3 sig figs. That's not enough. We need more than 10 milliliters. But too much would be more than 50 milliliters, because if you're using more than 50 milliliters, you have to refill the burette. And so this target mass is trying to get it between, let's say, 30 and 40 milliliters or something like that. Some reasonable volume and titrant. So we're going to weigh out 3 samples of this. We don't have to use desiccators. We don't have to dry it in the oven. These acid samples are fairly stable. Things like citric acid might be unknown, which is a solid in pure form, etc. So we don't know. There's a whole bunch of solid These are kind of big acids. Like acetic acid is a small acid, just 2 carbons. But when you get to like citric acid, malonic acid, maleic acid, those have a lot of carbons. And having a lot of carbons there means there's stronger intermolecular attractions between the molecules holding them together. So a lot of these are solid. Acetic acid in pure form is a liquid. That would be more difficult because, you know, measuring the volume of something like that and then, or weighing it might be difficult. But anyway, we're going to get at least 3 samples. We need 3 titrations. That agree with each other. But the problem is we're getting different masses here, so we can't use the volume this time. What we can do is we could use, let's say, the volume to mass ratio. And so this means we could do the calculations later. You know, the other thing is we could do the calculations now, but I'd rather not spend a lot of time on the calculations during lab. Calculations you can always do at home. And so what would be better is if we just, let's see, stand up. We just get the volume to mass ratio. And so for each run, calculate the volume to mass ratio. And then we want the biggest volume to mass ratio minus the smallest volume to mass ratio divided by the smallest volume to mass ratio times 100%. This will be the percent difference. And for the acid, I think we need a percent difference of 1%. Is that correct? Yeah. This percent difference, we want less than 1%. You know, of course, the smaller the better. I mean, if we get it within 0.5%, that's even better. And so we have to be conservative with our sodium hydroxide. You know, there's a chance you might run out because you might have to do a 4th. If you do a 4th titration, throw out the worst one. If you do a 5th titration, throw out the worst one. But hopefully you do not run out of sodium hydroxide. If you're concerned about the potential of running out of sodium hydroxide, decrease the acid sample size. So I would err, if it gives you a window, let's say 0.x to 0.y grams, I'd go closer to 0.x. You know, I wouldn't go big here. Even though going big is better because, you know, there's less relative error, you know, if you have bigger samples, but then we have to trade that off with running out of sodium hydroxide. All right, these acid samples, you know, if you spill some off the side of the balance, you just maybe I think I have, what's this brush? We used to have a little brush there, you could just brush it off. Or a damp, not a wet, but just a damp towel. A damp towel, you could wipe it up and just discard it. You could just discard it in the garbage, I think it's fine. Any questions? No. All right, that's all I wanted to say for today. So you can use all the time for the titrations.